Hello everyone. Here, I will introduce our work, EquiPose, exploiting permutation, equivariance for relative camera pose estimation. Relative camera pose estimation between two images is a fundamental task in 3D computer vision, which aims to estimate the rotation and translation between two cameras. It has a broad range of application, such as structure from motion, visual localization. Early relative pose estimation methods rely on feature matching, which generally employ a two-stage computational strategy. They firstly extract the correspondence using feature matching techniques, and then solve a two-view geometric problem accordingly. However, since the performances of these methods depend on the established point correspondences, their performance would significantly decrease or even fail in cases of weak repeated textures and degenerated configurations. Additionally, these methods could be time-consuming due to image matching and ransack loops. Moreover, they could not recover the scale between the two cameras. Recently, unlike the above strategies, many works have adopted deep neural networks to regress relative poses in an end-to-end manner. Compared with matching-based methods, they are more robust in challenging scenes with a significantly faster inference speed. Moreover, they could recover the scale of relative pose. Ideally, the estimated relative pose from image 1 to image 2 should be the inverse of the pose from image 2 to image 1, which we name as the pose permutation equivariance property. However, the PPE property is generally overlooked when designing model architectures in existing end-to-end methods. To validate this, we adopt two typical relative pose estimation model and visualize the inconsistency values of the rotation and translation respectively. The results on ScanNet are shown in this figure. As is seen, the pose differences, both rotation and translation, estimated by these models are generally larger than 0. Particularly, some of them are not trivial, demonstrating that the above models do not satisfy the PPE property. Such an issue may pose risks to downstream applications that require a stable and consistent estimation of relative poses, such as robotics and visual navigation. Moreover, it is also noted that some other visual tasks involve their specific equivariances, different from the PPE property in the relative pose estimation task. And once an existing model among these tasks is equipped with a task-specific equivariance, its performance could be further boosted. Motivated by the above issues, we investigate whether it is possible to explore such a relative pose estimation framework that could not only bestow the PPE property on various relative pose estimation networks, but also improve their performances further. Specifically, we first introduced the concept of PPE mapping, which refers to a mapping that captures the PPE property in relative poses. Then, we establish the foundational principle for equivariant relative pose estimation. Accordingly, we propose the EquiPose framework, which holds the PPE property theoretically. The EquiPose could improve the performance of a pre-trained model even without fine-tuning, and fine-tuning could enhance their performances further. The fundamental principle is that, given an arbitrary mapping F, which maps two images into the relative pose, we could construct another mapping F star such that F star satisfy the PPE property. This could be proved theoretically. Here is the computational pipeline. As is seen, the EquiPose framework could be implemented easily, just with several lines of code. However, it should be noted that such an implementation is twice that of the original model, which involves two forward propagation of network F. However, in practice, the computational overhead could be reduced further. Here is the pipeline of existing method, which involves two stages, namely the single image feature encoding stage and the cross-image feature decoding stage. When implementing the proposed EquiPose, we could reuse the extracted features. Thus, the additional computation from EquiPose is merely one decoding stage, which is SLY is most existing models. We conduct experiments on both indoor and outdoor datasets. We adopt 4 baseline models and evaluate their performance under EquiPose without fine-tuning and with fine-tuning respectively. The left and right tables reports the results on ScanNet and MapFree respectively. As is seen, a direct implementation without fine-tuning already improves the performance, and fine-tuning leads to a further boost. Finally, we evaluate the computational cost of EquiPose. This table reports the floating point operations and inference time cost of the baseline models and their implementation under EquiPose. As is seen, EquiPose only introduces slight computational overhead. That's all. Thank you for listening.